Have you ever heard of the Hertzsprung-Russell diagram? It's used by astronomers and astrophysicists to better understand stars, but also classify them and have a better idea on their life cycle. So let's see if we can have a look together. So when we are looking at the diagram, oh, it has vanished. That is exciting. There we go. Perfect. So when you have the Hertzsprung-Russell, it's quite a mouthful. So we have here, so when you are talking about the Hertzsprung-Russell diagram, it's a diagram that outlines, that puts stars with their characteristic. So if you look at this example here, I'm going to make this bigger. So you have here what we call the main sequence. The main sequence here has most of the stars in our universe. This graph shows about 22,000 stars that are classified with some characteristics. At the bottom here, I have the colors. So here I have 0 here from the bluish color all the way to the reddish color. And if you go at the top here, we go from temperature of about 3000 Kelvin with the red stars, going to 6000 Kelvin for yellow stars, and all the way to 30,000 Kelvin with the blue star. So here the color and the temperature are linked. Here we have cooler stars. Here we have medium temperature stars at 6000 Kelvin. This is where our sun is actually. It's the temperature of the surface of our sun. And then you have much warmer suns that are right here. Keeping in mind that if you have a star that is much warmer, much hotter, that means that the fusion reaction happening inside is going much faster. That means that stars that are right here, usually they will exhaust their fuel much faster than suns that are in the yellow color. With respect to the other axes, we have here the luminosity with the sun equals 1. So here our sun is right here. Then we have luminosity that are much weaker. So we have here white dwarfs that are very dim stars, to stars that can be up to 100,000 times more luminous than our sun right here. And on the other side, you have what we call absolute magnitude. So the absolute magnitude is that we take a star, we have a set distance from that star, and what will be the magnitude of the luminosity. So here, instead of looking at how the luminosity is from our Earth, which is called the apparent magnitude, we are given a specific distance so that we can all compare stars the same way. Good. So here, this is the first thing. So we have our sun right here. We know on the main sequence that some stars are less bright and cooler, reddish in color, and many more are much brighter, much hotter, and bluish in color. So you have to keep in mind that they get their energy from nuclear fusion. So we have nuclear fusion. So the most abundant material in our universe is hydrogen. And as you get to the formation of a star, we have a nebula. And the theory is that these materials are getting closer and closer, making the ball. And because of the pressure of gravity, we have more and more pressure. The temperature is increasing, and eventually it becomes a protostar, which is just before a star will lit. How does it happen? Is that because of the pressure and the temperature, we have a proton. So we have 2 atoms of hydrogen getting together, creating helium atom, so a new element, but it is also creating energy. And this energy is what we receive on Earth, the energy from the sun. So this is one reaction from one nuclear fusion, but knowing the immense quantity of hydrogen atom in the sun, that's what we receive all that energy. Now, keeping in mind that we have hydrogen and helium, but also as the pressure and temperature is increasing, we also have other atoms being created. As I mentioned, helium, we have some carbon, we have some oxygen. So what happens is every time you have different atoms getting together creating energy, then you have a star that is brighter. So here, if you go back to our drawing right here, you could see that we have our sun right here. We have here stars that are burning much faster given the energy coming out, and here we have less energy. The energy often is based on the mass of the original star. The, the bigger the star, the heavier the star, the more pressure and temperature we can get, the more gravity is available, and that's how we have different kinds of stars. Let's see, I'm going to get something here. So for the marker, perfect. Now, what else do we know about stars? So here's another drawing that is useful. So at the beginning, when you have a nebula, that is like the theory of a solar nebula, we have the material getting together and gets to a point where we have a protostar, and then we have our sun. Our star, the sun, is shining for 4.5 to 5 billion years. Perfect. Now we still have time. For another 5 billion years or so, our sun will shine with fairly uniform energy. But it gets to a point where when we have larger atoms merging together to create larger, how do we say that? Larger atoms, what happens is that you're going to have an increase of energy, and that increase of energy changes the way our star is. Because you have more energy being produced, a faster reaction, then you have more energy being produced, and that energy going outwards is competing with the pressure, and that energy becomes stronger than the pressure. So what will happen is that our sun, that is yellow, will expand and expand given the energy it has. But if you think of a very, very hot star about this big, and if you have a similar energy or just a little bit bigger, but a much bigger volume of a star, that star will become a red giant. And the reason for that is that you have a set quantity of energy with much bigger radius. So the temperature will be overall lower in the overall outside. So at some point, the reaction will stop, and then particles will go away, and what we're left will be what we call a white dwarf. So the white dwarf here is that in the core of that star, when we get the nuclear fusion, at some point there'll be more and more heavier atoms. You might end up starting with iron, and what happens when you create iron is that it's endothermic. It will get energy in to happen. Therefore, fusion will stop, and therefore you end up with what we call a white dwarf. So this is the French version here, but it is a very similar vocabulary. So we have our white dwarfs that will last for a long time, given that they are burning, they're very hot, there's a lot of fusions happening. However, it's so dense that it would take a lot of time for the energy to diffuse, and this can take tens of billions of years, even more than that. And then when they cool down, then you end up with red dwarfs, and then as the star will die. But this, from what we know, would take possibly 100 billion years, given that our solar system, our universe is about 15 billion years. From what we know, we haven't seen these red dwarfs from dying suns like ours. Now, there's something else that is interesting. This is our sun right here, which is a medium-sized star. If you have a much bigger star with a much bigger mass, what will happen? The cycle is very similar. So you get to a point where this is warm, but it will get even hotter. We'll get to a point where iron will be produced in the core, and what will happen is that as the energy will go out, instead of a red giant here for our sun, we're going to get what we call supergiant star. And what will happen is that the energy, once iron has been produced, will be endothermic. It will go in, the star will collapse, and by collapsing, there's so much energy, so much gravity. What will happen is that we'll have an explosion, and we will get a supernova. When you get a supernova, what happens is that we end up with a place that the temperature is lowering, and what happens is that you have a very dense core, and you end up with two options. If if the original star is maybe 10 to 35, 40 times the size of our sun, we end up with neutron star. Neutron star, there you go. And often another name for that would be pulsar, because they rotate very quickly and they send us light in not in a continuous way, but it's like a blip. It's very interesting. Or if the star is bigger than maybe 40 to 50 times our sun, then the supernova is leading to a black hole. And black hole being a part that it's almost an infinite gravity, an infinite mass given the size. And there's so much gravity here that even the energy from the light is absorbed. And when it's absorbed in the black hole, it can no longer go anywhere. The reason why I like the HertzSprung-Russell diagram is that it's a beautiful way to organize all the stars, knowing that the main sequence is where most of the stars are, and it shows that many of them are in the last legs of their life cycles. I know that I was looking at the news, they're expecting in the next bit, and that's relative, next bit could be a few days, few years, few decades, for a red giant, Betelgeuse, to explode and become a neutron star. It is, a lot of people are watching Betelgeuse. We'll see what happens. In the last couple of months, what happened is the intensity of that star has decreased, and we feel that there's something going on there. If it happens that you are interested, do a quick research with that. It's quite nice. So here we have someone, so we have a Pascalot, we have. So it swells into, let's see if I can put it here. So it's swelling into a red giant, flashing off the surface. It turns into gas clouds around it. So we need to get Earth out of the way. A shame it happens so much slow-mo. Very true. Interestingly enough, when our sun becomes a red giant, it will get so big that Mercury will be absorbed, Venus will be absorbed, Earth will be absorbed as well. So Earth will no longer be. But guess what? 5,000 years, 5 billion years from now is a long time from now. I don't know if humans will still exist. It's a big question. So with respect to our solar system, we're safe in our lifetime, which is a funny one. So the second question goes like this. So where does the explosion happen in a supernova, I wonder? A collapse of the outer against the inner core, or at the 0, within the star? So that's a good question. So let's see if I can do a quick drawing for that. So let's say that we are starting with a large blue star. So something that is probably more than 40 times the size of our star. When you have a star here, you have nuclear fusion. So nuclear fusion like this. So that happens, so we have the pressure going in because of gravity, like this. And then we have the energy from the nuclear fusion going out. This is no longer good. So we have the energy going out like this. So we have the energy. So during the cycle of the life of a star, this is even. It gets to a point where the nuclear energy from the nuclear fusion will get much bigger. So that blue star here would have a much hotter, more energy being produced. So it would turn like this, and then go like this. And that's when I call that we have a supergiant here. So a supergiant star will no longer be a bluish color, because given the energy and the much enlarged volume, it will turn into a supermassive supergiant star. So if I go here, that will be in this area here. It might turn yellow, unlike it could turn red as well, but we have supergiant star. Now what happens when you get to a point where there's one element and it is when iron starts to get produced in the center. So what's happening is that we still have pressure. So here we have pressure going in like this. And what happens is, because the creation of iron from two other atoms getting together is endothermic, absorbing energy. This energy that was moving outward the star is no longer there. So here you end up with, let's put this way, let's do this one, perfect. Good. Actually, let's see if we can start it over. You end up with a star that is like this. You have the pressure that is still there. But once you have iron, what happens is, because it's endothermic, you may have energy going out this way, but because this one is like an energy pit, what will happen? Energy will start going in. So here there's a situation. We end up with a lot of pressure in and so much less energy going out. So that creates a situation where this goes away. So you end up with a star that is shrinking. It goes in like this. So we have a star that is like this, will get smaller, and will get smaller, and will get smaller. And the consequence with that is the following. So I'm going to bring this much smaller. So when you get a much smaller situation, a few things happen. So you have the nucleus of the iron and the elements available, and you have the electrons that are traveling around. So the electrons are being pushed and pushed as close as possible to the nucleus. So you've got protons here and you've got neutrons there. They can push this way. The electrons want to have the atoms to be as far as possible. And it gets to a point where when the electrons are very close, then there's another shock wave that happens. The shock waves is that the electrons are so close to the nucleus, and there's no other way because there's so much pressure, that the electrons go with the protons and you end up, well, it's a bit complicated, but that's a simplification, but it will give you an idea. The electrons go with the protons and create more neutrons like this. So what happens is that you cannot have all this mass into one spot, because what happens, you have the pressure that keeps on building up. It gets to a point where the energy will be so big that it will just implode. It will go in and then it will just implode very quickly. When it implodes, a few things happen. You have the pressure in because of the implosion, and because we have things going on the outside like this. It's like action-reaction. This is moving this way, pushing even more in the inside. So all of this makes it so that we have in the middle a whole bunch of neutrons left, and then you have a nebula that is all around with all the different pieces from the star. And this is what we call a neutron star. Everything is so dense, but still it spins and we can still see them through space. We call them pulsar, because if you have something that spins like a lighthouse, the light will come to you when it's towards you and then will go away when it's on the other side. This is our neutron star. Now the other question is that if we have an even bigger stars, what happens is the gravity has been so big and the explosion of the supernova has been so big that even the neutrons here, they got even more squished this way. And it gets to a point where, right here, we don't really know what is happening here, because you end up with a 0.00, as you mentioned in your question. Right here, you have a mass that is almost infinite with an infinitely small space. All we know here is that you have a spot, and if it happens that you have matter going close by, it will be attracted by this very dense and very high gravity field. And even rays of light will be redirected towards that. And if the rays of light gets too close to a black hole, then all the light are gone. And that's more or less how we called it being a black hole. And some of you say, well, how do we know? Why do we call them black holes? I'll share that. So the whole idea was if you have star so stars are in space, we have the background that is black. And the issue though is that if you have an object that is black like this and goes in front of the star, then we no longer see the star. So somehow it's like this black, something black going this way. We also know that when you have a black hole that is, let's say, close to a star, sometimes you have rays of light that change direction. So here, let's say that you have your black hole here, you have a change of direction of the way that the star looks. Sometimes the star is almost all gone, but you can still see light rays because it is changing direction because of the black hole. We call it a black hole because we see nothing where they are. Is it an original name? Far from that. But it's quite interesting anyway with respect to how we name black holes and what happens from a star that explode, and there's so much matter that it changes matter completely. So, Pashkalat, excellent question today. Thank you for adding to the stream today. And that will be our second segment today. If you've enjoyed this segment about life cycle of stars, please don't hesitate to subscribe to our channel. Put any comments, clarification, questions. I'm here for you. And I'm going to share with you another, another video about stars and astronomy. I think I'm going to use, I did a video on a probe called the Parker probe. It's a probe that is in orbit around the sun, and it goes into cycle, and we get amazing photos and amazing data. So I'm going to see you in the next video about the Parker